All right, grade 12 chemistry. Let's talk about acids and bases. Here's what we're going to talk about today. First, we're going to learn a new theory, potentially for most of you, the Bronsted-Lowry theory of acids and bases. Then we'll talk about conjugate acids and bases, which exist in the Bronsted-Lowry theory. We'll talk about some equilibrium constants, Ka, Kb, and Kw. We're going to use those to calculate pH, and then we'll talk a bit about how salts will affect the pH level of a solution. Getting right into it, we're starting with talking about this Bronsted-Lowry theory, and this is, for a lot of you, is probably going to be a new theory of acids and bases. Some of you might have seen it before. Essentially what it does is it expands on the Arrhenius theory of acids and bases. Quick review from grade 11. Strong acids versus weak acids is the first thing I want to talk about. So in grade 11, we say that strong acids are fully dissociated in water. So for example, HCl, when you put it in water, it is fully H plus and Cl minus is what we say. Meanwhile, a weak acid, like say vinegar, which is acetic acid, is only some of the H plus comes off and the rest of it doesn't. And here's some examples of some strong acids and strong bases. This is the classic Arrhenius, right? H marks an acid, OH marks a base. That's the Arrhenius theory. And all of these are still going to be acids and bases in our Bronsted-Lowry theory, but we'll see some more interesting examples of acid-base chemistry. And there's also the pH scale. You guys might know it as going from 1 to 14, and that different things have different strengths. Some people get weirded out that milk is actually slightly acidic. Well, it is. That's basics of acids and bases. Let's get into our new stuff. So here's Arrhenius, right? Arrhenius, and I'll take this away. Arrhenius acids and bases. This is Arrhenius. This is his face. Put forward the theory in 1884. It was the first chemical theory of acids and bases, which said that acids have hydrogen ions in them. Hydrogen ions. Ions were a pretty new concept back then too. And bases have these hydroxide ions in them. That's the Arrhenius theory of acids and bases, that there's an actual chemical structure for acids and bases. This was revolutionary at the time because they had just started decomposing things into individual ions, and they were playing with electricity and stuff like that. So it was a big deal for Arrhenius. Arrhenius had a lot of cool kind of revolutionary ideas. He was in the right place at the right time to put forward a lot of fundamental chemistry. But this fails to explain some other things. Like, for example, the Arrhenius theory, this H plus OH minus thing, doesn't explain why carbonates, like baking soda or limestone, why they're basic. We know that they are. If you put vinegar and baking soda together, the vinegar is clearly an Arrhenius acid. It releases H plus, but the baking soda is a carbonate. There's no OH minus there. Why do we get an acid-base reaction? So that doesn't explain it. It also doesn't explain why ammonia, which is NH3, is a base. There's no oxygen in ammonia. There's no way to make OH out of it. So why is it a base? Well, this is what Bronsted-Lowry, that's what the Bronsted-Lowry theory is going to do. It's going to expand our definition of acids and bases to include things that aren't just Arrhenius acids and bases. But just as a reminder, all of those Arrhenius acids and bases are going to be able to act as Bronsted-Lowry acids and bases. First, though, let's talk about that strong acid, strong base stuff. Strong acid and weak acid, strong base, weak base. Fully dissociated versus partially dissociated sure sounds like an equilibrium concept, doesn't it? And it is. Right? HCl will dissociate into H plus and Cl minus in water, but there's nothing stopping that H plus and Cl minus from coming back together. They're positively and negatively charged. They're going to come back together and meet each other and get together. Problem is, they'll very quickly get ripped back apart. But there's always a little bit of this stuff, H and Cl together, those two ions together, in the water. And we can figure that out using some, fancy chemistry. And it works out that you can get an equilibrium constant because there's a forward process, the HCl dissociating. There's a reverse process, the H and the Cl getting back together into HCl. And so you get an equilibrium constant. All of these are aqueous, so they all factor in. Turns out it's about 1.3 million. It's a very big K. It's a very big number, which means that there's not a lot of HCl and most of it is H plus and Cl minus. So that's why we call it a strong acid. It is mostly on the product side of the reaction. And we know that a big K means it's mostly on the products. A small k means it's mostly on the reactants. So vinegar, acetic acid, has the same kind of thing where it dissociates into H plus and acetate here. But the equilibrium constant is 0.000018. So it's mostly the acetate and a lot less of the mostly the acetic acid and a lot less of the acetate and the H plus. So they're more likely to be together than they are to be ripped apart. So that tells us K is very big, products are favored, K is very small, reactants are favored, and so a strong acid will have a big K value, and a weak acid will have a small K value. So kind of a cool little aside there. So this K value has a special name. This is the Ka, acid dissociation constant, where the H and the Cl fall apart, or in this case, the H and the acetate fall apart. If you do the math, right, H plus times Cl minus, it's kind of squared, so you kind of square root this, and you come up with about 1 in every 1,000 HCl molecules is together, and the other 1,139 are apart. Bases, similar thing. Base dissociation constant falls apart. It's the Na and the OH. It's also quite a big value. So it turns out, and this is the weird new thing, turns out that H plus isn't actually stable. It's a single proton. So it's not actually stable in water because it's so positively charged and it's so small that it really wants electrons, right? Think about the electrical environment there. It's a single positive proton with nothing around it to shield its charge, so it's going to pull electrons very strongly. So what actually happens is that proton will interact with one of the lone pairs on water. It'll pull that lone pair, it'll pull those electrons and turn them into a bond. And this creates what we call the hydronium ion, H3O+. That's the hydronium ion. So H plus doesn't actually exist. When we write something like this, H plus, what we really mean is hydronium. There's always water around for the hydronium to form with, so it's just a shorthand of H plus means hydronium. But yeah, that's the hydronium ion. And this is where we're going to get our new definition, our Bronsted-Lowry definition, is that here when HF dissolves in water, the hydrogen isn't just free floating, it attaches to water and makes hydronium, which makes this a chemical reaction. And so the water is actually pulling the H plus away from the hydrogen fluoride. The hydrogen fluoride is giving up an H plus, the water is accepting an H plus, and it's actually turning it into a new thing, hydronium. And that's going to be the new definition. Acids will transfer their hydrogen to something else. And this means that acids and bases will only exist during a reaction, right? This has to happen during a reaction. This hydrogen has to go somewhere. It's not just free floating. It actually has to go and attach to something. And so acids and bases only work if you can see it during a reaction. You can't just say something is an acid. You have to say it acts as an acid when it's meeting something else. And that's why I said act as Bronsted-Lowry. So that's where we get Bronsted-Lowry. Here's Bronsted and here's Lowry. They're Norwegian, I think, hence the O like that. I think it's Bronsted. I'm not sure how to say it. But that's the Bronsted-Lowry theory, that the acid in a reaction, so I should really say in a reaction somewhere in here. Let me just type that out. In a reaction, and it has to be in a reaction, acids release H plus and bases. Acids will release the H plus, so that's like Arrhenius, but bases will absorb H plus, and that's the new idea. It explains certain things. I remember I talked about how Arrhenius can't explain why baking soda or ammonia is basic. Well, here's ammonia and here's water. Ammonia has an extra lone pair. There's a lone pair of electrons on the nitrogen there. And then the water will actually give its proton to the ammonia to make the ammonium ion. And then it leaves behind hydroxide, which, as you guys know, it kind of makes a base. So ammonia is basic because it pulls that hydrogen away. There's a demo of it. There's a structural thing of it. It'll literally pull the hydrogen away. And so the ammonia is absorbing the H+. It's a base because that's what Bronsted-Lowry say. Bases absorb H+. But what's releasing the H+? Well, it's actually the water itself. The water itself is giving up an H. So the water is the acid in this reaction. You might not think of water as an acid, but in this reaction, water is being an acid. So that's the thing about Bronsted-Lowry. It only makes sense if we think about acids and bases in a reaction. Now we're getting into conjugate acids and bases, so I'm going to pause for a sec, and we'll talk about those. All right, so we've seen Bronsted-Lowry acids and bases. We've seen this exact thing diagrammed. NH3 plus H2O makes NH4 plus OH minus. So the ammonia grabs the hydrogen off of the water, makes ammonium, and leaves hydroxide. But this has an equilibrium arrow. So there's a forward and a reverse process. So in the forward process, the hydrogen goes from the water to the ammonia, right? And that's the forward process. The hydrogen goes from water to the ammonia, which makes the water an acid because it's giving up an H+. Acid. Right, that's acid. And the ammonia is absorbing an H+, that makes it a base, a Bronsted-Lowry base. But let's think about what happens. This is an equilibrium arrow, so there's a reverse process as well. In the reverse process, I'll do it in green, we start with ammonium and hydroxide, and we end up with ammonia and water. So in the reverse process, this hydroxide is going to go back and attach, this hydrogen is going to go back and attach the hydroxide, making water. So in the reverse process, the ammonium is acting as an acid, and the hydroxide is acting as a base in the reverse process, right? In the green arrow, which is going the other way. This is where we get the concept of conjugate acids and conjugate bases. And as I just showed you, an easy way to identify them is to flip the reaction and see what's happening with the hydrogen. For an acid to release a proton, something has to absorb a proton, which means that every acid needs to have a base and every base needs to have an acid. There's no way to just get a free proton. That proton has to go somewhere. That H+ has to get attached to a molecule somewhere. It's not just going to be free floating. And so we write the expression however we want to write it. We could write this backwards if we wanted to. And the one that we have on the left side is going to be the base and the acid. The one on the right side is going to be called the conjugate acid. I'm just going to write CONJ for conjugate. You can see the spelling down below, right down here. Conjugate acid and the conjugate base. So it's important that what was the acid on the left side, what's left behind is the conjugate base. What was the base on the left side, what's left behind is the conjugate acid. Right? It kind of reverses. Right? I actually have this wrong. The conjugate acid is the substance that the base turns into. And the conjugate base is the substance that the acid turns into. Right, that's another way to think about it. But the easiest, if you want to get it 100% right every time, just flip the reaction and see what happens. Right, on the green side, this becomes an acid. On the purple side, this is the acid. And here's the general formula. Right, general formula: HA plus B to A minus plus HB plus. Let's talk about water. Water being weird. Here's an acid, HCl. Here's water. The H goes to the H2O, making H3O plus. That means water is absorbing the H plus, it's being a base. The HCl is being an acid in this reaction. Fair point, fair enough, right? Which means we have a conjugate base of Cl minus. But here, calcium carbonate, the hydrogen is going to go from the water to the carbonate, making bicarbonate, meaning the water here is acting as an acid, leaving behind OH minus as its conjugate base. The calcium ion doesn't actually do anything. Ca2 plus doesn't actually do anything, and the conjugate acid is this HCO3 ion. So that means that water is a base. Here, water is an acid. Water can be an acid or a base depending on the reaction. If there's an acid in water, the water is going to be a base. If there's a base in water, the water is going to be an acid. So here's a few examples of this, just so we get an idea. I'll do one, and then we'll do the rest in class. So here's whatever HCHO2 is, plus H2O, and it turns into CHO2 minus and H3O. So let's think about what happens to the hydrogen. Well, this becomes H3O from H2O. So that means that one of these hydrogens must have transferred over to the water. There's the H plus moving. All right, the H plus is moving, which marks this as an acid, right, and this as the base. Water here is being the base because it's absorbing the H plus. This is giving up the H plus. Now, if we go on the other side, right, on the other side, this H3O plus and this CHO minus, H3O plus is the conjugate acid here, the conjugate acid, because if we go the other way, it's going to give that H plus back so that the H2O gets regenerated. So this becomes the conjugate base, and that's what we predict. So we can, you can see that. And the same thing with all these other ones. Typically OH minus is going to be a base. Typically H3O plus is going to be an acid. So you can probably assume that this H3O plus is a conjugate acid. It doesn't want to gain any more hydrogen. It's positive. It really doesn't want to gain hydrogen. So that's a concept that you can use as well. So that's conjugate acids and conjugate bases. All right. Next up, we're talking about KW, Ka, and Kb. So I'm going to pause and get that set up. So we've established now that water can act as an acid or a base, or if we want to be a bit more specific, like acid and base nature depends on the reaction, not the substance. So here we're going to talk about amphoteric or amphiprotic. Those are both words for the same concept, substances. Water, we've seen, can gain an H plus and become H3 plus, or lose an H plus and become OH minus. It means it can be an acid or a base, depends on the circumstances. We talked about how if an acid, a stronger acid, dissolves in the water will absorb that acid's hydrogen and become a base. If a stronger base dissolves in the water, the water will give up the hydrogen to that base and it'll become an acid. The water will become an acid. This is a property called amphoteric or amphiprotic. Both are used interchangeably. Amphiprotic, I think, is probably the one that makes the most sense. Amphi, like two, and protic, like proton, right? You can proton different ways. So here's some examples of it. Bicarbonate ion is a classic example of this. In a strong acid, it can pull an H plus. It's already negatively charged, so it'll pull an H plus. It'll make H2CO3. H2CO3, that's a conjugate acid. In a weaker acid or a base, remember that it depends on the reaction, it'll act as an acid. It'll make CO3 2 minus. It'll give up that hydrogen that it's holding on to. It'll make conjugate base. So that's an example. Another one is amino acids, which we've talked about previously, and in biology we talk about this a lot. The different amino acids, the NH2 can absorb protons, so it can pull in an H plus as a base, become NH3 minus. Pull in a proton, become an H3 minus. That'll happen when there's a lot of H plus around. So it happens at low pH. All right, there's a lot of H plus around, they'll go on to the NH2. If there's not a lot of H plus around, it'll go the other way. And the NH3 will give up H plus and become back to NH2. There's also the acid part of it, the carboxylic acid part of it. It can release a proton. And become negatively charged. So if it releases a proton, it's an acid, which happens typically in more basic solutions. In a very acidic environment, this thing will actually act as a base. In the middle pH range, you get what's called a Zwitter ion, where it's holding a positive and negative charge at the same time. It's a German term, Zwitter ion. I think Zwitter is like kind of glitter or whatever. It's like both at the same time. Very cool. So that's an amphiprotic substance. And again, it depends on the environment. Here's water acting as an acid. Here's water acting as a base. And in fact, this is also bicarbonate acting as a base or bicarbonate acting as an acid. So this will happen depending on if there's a stronger acid or base in the water. Right. If there's, I don't know, HCl in the water, you've got a very strong acid, then this thing's going to act as a base. And it'll pull that H plus out of the water. If there's a strong base like NaOH in the water, this bicarbonate will release its H plus and act as a conjugate base. It's very neat. This is important for buffer systems. We'll talk about buffer systems in a future video. We talked about Ka because it's a reaction. There's an equilibrium here, and in water, one of the reactants is always a liquid, right? So the acid plus water gives H3O plus and A minus, so we get this Ka. I should really put that A in there. Ka, which is the concentration of H3O plus times the concentration of A minus over Ha. So that's Ha. We pretend often that hydronium is just H plus, so it makes the thing a lot simpler, makes the reaction a lot simpler. We just kind of ignore the fact that the water is here and that's making H3O plus, and so you get kind of this setup. There's also Kb. You get a base dissociation constant. In this case, it's absorbing the H plus, and so we're looking at it's absorbing the H from water, making hydroxide. So it's going to be the concentration of hydroxide and the concentration of the conjugate acid over whatever the base was, over the concentration of the base. Right, so that's the kind of concept here. And then strong and weak, we talked about that. But then we get to water. Now water is amphiprotic, right? Water can act as an acid, it can act as a base. The really weird thing about water is it can act as an acid and a base to itself. And that is incredibly strange. The best way I can explain this is to diagram it. So let me diagram water acting as an acid and a base at the same time. So what happens is I'm going to draw two waters. Here's H2O. And I'm going to draw another water. I'm going to draw it in red just so that we can see it a bit better. And as you know, there's a delta negative, delta positive kind of thing going on. Right? And there's these lone pairs. So what can happen is if these things bump each other just right, maybe they bump each other like this, right? Bump each other like this. I guess I should move this. Right, they bump each other like that. They collide like that. You can end up with an interaction where that red hydrogen is now very close to this oxygen. It will actually hop right over, and what you end up with is a hydronium ion like this, and a hydroxide. Right, and hydroxide. And that's what we're seeing in our expression over here on the screen. Two waters come in and you end up, they self-ionize. And so you get an equilibrium constant. These are aqueous, this is a liquid, we ignore it, so it just becomes H3O plus times OH minus, or H plus because we can shortcut that. And we can calculate that. It is 10 to the minus 14. 10 to the minus 14 in room temperature water. and that's called Kw. It's a very important one, so it gets its own special subscript. It's the equilibrium constant of the self-dissociation of water splitting itself into H plus and OH minus, well, H3O plus and OH minus. That's 10 to the minus 14, very, very small. That means H plus times OH minus is 10 to the minus 14. If you want to find in neutral water, if H plus is going to equal OH minus, that's like X and X, so it's X squared. You square root it, you get 10 to the minus 7. If you think about your exponent rules, right? Square root of 10 to the minus 14 is going to be 10 to the minus 7. So about 1 in every 10 million water molecules is split at any given time. And then when the H3O plus meets the OH minus, you can go the other way. That's why I wrote the equilibrium symbol here, right? When these two meet, they can go back to being two water molecules. So about 1 in every 10 million water molecules has been split in this way, in any kind of water, neutral water, which is kind of weird. Like I'm drinking some water right now. I know that there's some H plus and some OH minus in there from water interacting with itself. Profoundly strange. So what does this mean for us? Well, this is going to get into pH, and that's our next topic. So I'm going to pause. I'm going to set up the pH lesson. So this Kw stuff, this dissociation constant of water, brings me to pH. You might have heard, well, you probably know that the neutral water has a pH of 7. And this constant, Kw, is 10 to the negative 14, which means in neutral water, it's 10 to the negative 7 moles per liter of H plus, well, H3O plus, which is the concentration of hydrogen, of hydronium. What that means is that in neutral water, 10 to the negative 7, and that's pH of 7. The 7 being the negative 7 is not an accident. That's literally what pH means. pH means power of hydrogen. Power of hydrogen. Big H, right? Big H for hydrogen being hydrogen. And it's literally the power. Is that 7? It's the negative. But yeah, that's what pH means. It's very cool. pH of 6 means 10 to the negative 6. Now it's a smaller negative number, so you've got a higher concentration. Negative 4, another higher concentration. That's why lower numbers mean a more acidic, because there's more hydronium. There's more of this H plus in the water. Which of course means you can go below 0 pH. You can have a pH in the negatives. Our lab acid is 10.7 molar HCl, and it ends up having a pH of negative 1 point something. Which is pretty cool. Yeah. So, and you can also have a pH of above 14. That's also entirely possible. So to calculate it, there's this thing up here. pH is the negative log of H plus. It's easy for like 10 to the negative 5, that's pH of 5. 10 to the negative 9 is a pH of 9. But partial pHs are a little bit more interesting. What if the concentration is 0.2? That's 0.1 would be a pH of negative 1. 1 mole per liter would be a pH of 0. But 0.2 is going to be somewhere between 0 and 1. And so here's the equation that's used most often, negative log 10 of H plus. The logarithm function, if you haven't taken advanced functions yet, the log 10 function tells you what power of 10 gives you the number you're looking for. Now in my calculator, I'll pull it up on my calculator, I've got a log button. It just says log over here, log. That is by default log 10. That's what the log button on my calculator does. And so this pH then, which the 0.2, we said it was between 0 and 1, because a pH of 1 would be 0.1, pH of 0 would be 1 mole per liter. The pH is 0.69, because if I put in my calculator log of 0.2, if I put in log of 0.2, I actually get minus. Right? If I put in log 0.2, I get minus 0.7. But that's why we put it to the negatives, just to have a positive number. So if I put negative log of 0.2, there's my 0.7. Negative log of 0.2, 0.7. So that's how we calculate pH. You can have negative 1.3. 2 moles per liter would be negative 0.3. 4 moles per liter would be negative 0.6. You might have actually used some of these, like 2 mole per liter HCl, in a lab at some point in grade 11, and you were using something with a negative pH, and you didn't even know it. Right. Then there's POH. It's the inverse of pH. It's the hydroxide concentration. It's done the same way. So POH is negative log of OH, and you can in fact have a P of any substance, P of, I don't know, like CO3. You can have PCO3, you can have P, I don't know, ammonia, whatever. And the way that power laws work out, we know that the concentration of H plus times the concentration of OH minus is always 10 to the negative 14. Right? We have this concept, H plus times OH minus is 10 to the negative 14. So pH times POH, pH plus POH, because when you multiply exponents, they add. pH plus POH is always 14. Going the other way, if you want to know, go the other way, you use this 10 to the power of concept, right? If it's 10 to the negative 6, that's pH of 6. So if you have a pH of 5, it would be 10 to the negative 5. If you have a pH of 5.5, it would be 10 to the negative 5.5, and stuff like that. And then using that concept, you end up with an interesting relationship for a substance. If you have a strong acid, you end up with a weak conjugate base. And you can rearrange the Kw equation, that the dissociation constant, the acid dissociation constant times the base dissociation constant is the water dissociation constant, 10 to the minus 14, which means if you have a strong acid, it has to be a very weak base. That same substance has to be a weak base. If you have a strong base, it has to be a very weak acid. If it wants to give up an H+, it's not going to want to pull in an H+. If it wants to pull in an H+, it's not likely to give up an H+, is another way of saying it. But there's a mathematical relationship, and it's based on Kw. It's very, very cool. Yeah, strong acids have weak conjugate bases. And our strongest acids are very weak conjugate bases, and our strongest bases are weak conjugate acids. I'll talk more about this in class. So, for example, if you want to make a really strong acid, you just want to make something that will absolutely not ever want to pull in an H+. Never, 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 never. So you probably want something with a lot of hydrogens on it that doesn't want another hydrogen. That's very likely to give up a hydrogen. If you want to make a strong base, you want something that really wants hydrogen. So some of the strongest bases are stuff like butyl lithium, where it's lithium minus. It's butane with a minus on it. So it really wants that hydrogen. Very, very cool. And the last section is salts and pH, using this concept of strong acids have weak conjugate bases and weak acids have strong conjugate bases. We can talk about the effects of salts. I'm going to pause for a sec to get that set up. So here's our last piece. It's salts and adding salts to water. And it's easiest to explain this stuff when we talk about Le Chatelier's principle, because this is based on Le Chatelier's principle. And this is what you have to remember. You have to remember that a strong acid has a weak conjugate base. So if we put just the weak conjugate base in, nothing's really going to happen because it's a weak thing. It doesn't really want to pull in hydrogen from anywhere. And the other thing we have to remember is that water can either give up a hydrogen or pull in a hydrogen. So, here's an example. We put NaCl in water. Here's HCl dissociating to H plus and Cl minus. We know that this is very strongly favored. We know that this is very strongly favored this way because HCl is a strong acid. So Cl minus is a really, really, really terrible base. Cl minus would be the base. It would absorb the H plus, right? But it doesn't want to. We're putting in this really bad base. Now for this one, sodium hydroxide, we know the same thing. We know that sodium hydroxide with water is a very, very, very favored to go this way, leaving the sodium in the water and absorbing an H+, which means the sodium doesn't really want to absorb an OH- from the water. It doesn't want to pull one out. So sodium's a terrible acid and chlorine's a terrible base. And so we put sodium and chlorine in water, not a lot happens. But if we put something like sodium acetate in water, this, the sodium part, the sodium is still a terrible base. Sodium's still a terrible base. Sodium's a terrible acid. My bad. Yeah, terrible acid. Chlorine's a terrible base. Sodium's a terrible acid. A very bad conjugate acid. But acetate is the conjugate base of acetic acid. Now, acetic acid is a weak acid, which means that acetate is actually a relatively decent base. It will pull hydrogen away from water. It will pull hydrogen away from water to generate acetic acid in the water, which means since it's pulling the acid away from the water, it shifts that H plus OH minus balance, and you'll end up with actually making a basic solution. Even though you're not putting in an acid or a base, you're putting the ions. Ammonium chloride's the opposite example. Chlorine is a very, very, very terrible base, right? We've talked about that. Chlorine does not want to pull in hydrogens from water. But ammonium can give up its hydrogen relatively easily because of the conjugate acid of a weak base. And so NH4 plus ammonium is a decent-ish acid. It's nowhere near as good as like HCl, which will fully dissociate, but the NH4 will dissociate somewhat. Yeah, and this explains why sodium bicarbonate, like baking soda, it's a base. Sodium is the conjugate acid of NaOH. NaOH is a very strong base, and so its conjugate acid is weak. So sodium is a weak acid in water. Bicarbonate is the conjugate base of carbonic acid. Carbonic acid is a weak acid, so bicarbonate is a okay-ish base. But compared to the sodium, it's a pretty good base, and so you end up with a basic solution when you put sodium bicarbonate in water. This is why sodium bicarbonate is basic. We'll do a bunch of practice problems with this when we get to class. Yeah. And the last little piece here is this statement about that. And that's that because weak acids have strong conjugates, right? Weak acids have a strong conjugate base. Weak bases have a strong conjugate acid. The absolute weakest acid you can have in water is the water, right? Because water by itself, by definition, is neutral. That is the weakest we can get. So because water is the conjugate base of H3O+, and water is the conjugate acid of OH-, H3O+ is the strongest acid in water, and OH- is the strongest base in water, because their conjugate, the conjugate is water, which itself is neutral. Which tells us that if a Ka of an acid is bigger than 55.6, I can explain where that comes from, where the 55.6 comes from. It's the molarity of water in itself. Then it's going to be fully dissociated. So HCl being about 1.3 million is way bigger than that, 55.6. We can assume that it's fully dissociated. It is fully an H3O+. Same thing with NaOH. And then the last piece is this stuff called pKa and pKb. Instead of just Ka, you can just use the P thing and do negative log 10 of it, and you end up with pKa and pKb. And this is used a lot in organics to talk about how easy it is to pull hydrogens away from things. It becomes an important thing in organic chemistry. But that's bonus content. You can look that up if you want, but it's linked to Ka and Kb by the same same equation as pH. So we've talked about Bronsted-Lowry theory of acids and bases, where acids give up H+, but bases absorb H+. In Bronsted-Lowry, bases no longer just have OH-, they actually absorb H+. You got conjugate acids and bases, figuring out what's the conjugate, Ka and Kw and Kb, the water self-ionization, and then calculating pH and pOH. So what does the pH actually tell us about the concentration of H+, or the concentration of OH-? The last piece was salts, putting in salts and how they affect pH. That's it for today. Thanks for paying attention, and I'll see you guys in class.